All right, so we are recording lecture now. So good afternoon, everyone. This is IC242 Continuum Mechanics. This will be our 19th lecture, and today we'll be talking about deformations or strains. So the agenda for today will be first we'll start with we will do a quick recap from last time. So we'll do a recap of configurations. We'll talk about the two ways configuration can change as we discussed last time. Then we'll also quickly recap material coordinates. And as well as spatial coordinates. So that will be the recap from last time. Then we'll talk about displacement field. Post that, we'll talk about the Lagrangian and Eulerian description of motion. And then finally, we'll talk about the material derivative. So material derivative will be the highlight of today's lecture. All right, in terms of announcements, we have one. So I have uploaded the solutions to problem set 3. And problem set 4, I thought of uploading it last week on the weekend, but I realized that we still need to discuss a few more things before I can upload it. So let's discuss a few more concepts from kinematics, and then I will upload the solution. Then I'll upload the problem set 4 for you to try. So most probably you'll have it online either tomorrow or day after tomorrow. All right, so before we start, do we have any questions from the previous lecture? Or any questions in general? All right, so if there's no question, then we'll start. So in the previous lecture, we developed some terminology to be able to describe the motion in continuum mechanics. Now we said that when you have a collection of particles which describes a body, which could be a solid body or a fluid body, we will be talking about solid bodies first because they are more intuitive to discuss when discussing continuum mechanics. So if you talk about a configuration, then we said that a configuration is nothing but a collection of particles in a certain way. So if you have, I mean, in a typical solid body, you will have infinite number of particles. So if you label them, hypothetically, if you labeled all the infinite number of particles, then the configuration is the way they are oriented with respect to each other in space. So we have a configuration where you have a collection of material particles. So these are now. Then we said that if you apply some stress field on the body, which we're not interested in this particular discussion, but after doing that, the body may move. So the motion of the body can be split into two major parts. So one we call rigid body motion, and the other we called call it as deformation. So the body that I've shown here, it may move as a whole, it may rotate. So that's rigid body motion. So we call it its translation plus rotation. So translation and rotation together, they form the rigid body motion of a particle of a body. Now deformation, on the other hand, is when the body changes shape and size. So what that means is that the body may not move. The body may just, the center of mass may stay there, but the particles will change their position with respect to each other. All right, so if you have a ball, you try to compress it, then you may just change the size of the ball, you may just compress it as a whole. Even then, the relative distance between particles has changed. And if you just take a ball and apply some shearing, so you take the ball and you shear it, then you will see that the ball may not remain spherical, it will change shape, and that is again deformation. In continuum mechanics particularly, we are interested more in deformation rather than rigid body motion. So if we have motion as a whole, then we tend to remove the rigid body motion from it and just study the deformation. But for now, all we need to know is that motion can be split into two parts, rigid body as well as deformation. Okay, then in the last lecture, we also talked about something called material coordinates. Which we denote as the capital X vector. So material coordinates, they refer to the, in most of the cases, they refer to the position of the particles at t equal to 0. So that's what we call the reference configuration. So in the reference configuration, the coordinates of the different particles are together known as the material coordinates. All right, so the other thing we discussed was spatial coordinates. Which we denote using the small x vector. So spatial coordinates, they refer to coordinates in space. So they are fixed in the room or the space coordinate system. Now different particles may pass the same spatial coordinate depending on how the body is moving. So depending on the spatial coordinates as well as a given current time, you will have certain particle sitting on that spatial coordinate. The spatial coordinate system is a coordinate system which is fixed to the room or the spatial to the space. So as an example, if I take a certain coordinate, let's take this coordinate 1, 2, and then I have the body which, so the initial one is the initial of the reference configuration, and then I have the body move to some other configuration, which is at time t equals t1. So what we see is that at t equals 0, which is reference configuration, we had a particle A here, which has moved to small a in the current configuration. So 1, 2 in the material coordinate system will always refer to particle A. Okay, no matter whenever you talk, 1, 2 in the capital X coordinate system will always refer to particle A, because by definition it is the position of a particle at t equals 0. Whereas if I talk about 1, 2 in my spatial coordinate system, then depending on what time I'm talking about, so we'll have different particles pass through the same point 1, 2 at different times. It's very important we understand the difference between these two. So again, a quick summary. So material coordinate system, which is denoted by capital X, it refers to a coordinate system, or it's fixed to a configuration which is at t equals 0. So if I give 1, 2 as a material coordinate of the body of some particle, then it always refers to particle A. I may talk about material coordinates 1, 2 at different times. Even then, it will always refer to particle A, because by definition, 1, 2 in material coordinate system refers to the particle, the body at t equals 0. Now in the spatial coordinate system, it's always fixed in space. So what you do is at 1, 2 in the space, you fix a probe, and then you see which particle flows through it. And sometimes you may have no particle at 1, 2 in space. So spatial coordinate system refers to coordinate system which is fixed to your room or space. So we'll use this again and again, and the idea will get reinforced in time. It's also very common to think of material coordinates as a coordinate axis which is attached to particles. Because when I say 1, 2 in the material coordinate system, it's always referring to particle A. So it's as if I'm attached to particle A, and I follow the situation of particle A in time. Whereas spatial coordinate is attached to your room. Okay, so your spatial coordinate system is attached to your room. All right. So then we talked about the specification of motion of a body. So what we said was that the motion can be specified using a function. So I can specify my spatial coordinates as a function of material coordinate and time t. So what that means is if you specify some material coordinate, which basically refers to some point, because remember material coordinates refer to points at t equals 0. So if you specify, for example, 1, 2 here, then that means you're talking about particle A, as we discussed previously. So a chi of A, t simply will refer to where exactly is A at this time t. So if I go back, it will end up giving you the spatial coordinate of this point small a, because small a at t equal to t1 has moved to, sorry, capital A at t equal to 0 has moved to small a at t equals t1. So the spatial coordinates of capital A at t equals t1 is the spatial coordinates of small a, whatever they are. Okay, so this chi function helps us understand how the body is moving, because capital X as a whole, as a field, will refer to all the particles or the complete body, and this function chi, which has information about how all the particles are moving in time, will tell me how the body is moving, which comprises of the body deforming as well as the body moving as a rigid body. Okay, so the complete motion is contained in this function chi, which is also written as x. Okay, so this chi function or the x function is the most important function in kinematics. It contains all the information about motion in the system. And we also discussed that we can define something like an inverse function. So what that means is capital X can be written as chi inverse of small x comma t. So what this says is you give me a spatial location and you give me the current time, and I'll tell you which particle is present at that particular spatial position, or which the position of that particle at small x at time t at t equal to 0. So capital S always denotes position at t equal to 0. Now, the inverse function may not exist all the time. So we say that the function chi is invertible if the Jacobian is not 0. Okay, so what that means, Jacobian is defined as, so we're talking about a transformation here from capital X to small x. So Jacobian is defined as a determinant of del small xi by del capital Xj. So you can see that del small xi by del capital Xj is a matrix, and the determinant of that matrix is called the Jacobian. So you're transforming from one coordinate system to other coordinate system. This in the expanded or the matrix form is written as so this determinant should not be equal to 0 if we want the function chi to be invertible. Okay, so that's coming from your mathematical ideas. Okay, so that's pretty much what we did last time, and now we'll start fresh discussion on Lagrangian and Eulerian coordinates. All right, so let's think of a physical property. Let it be density. Okay, now we can express this density as a function of capital X and t. So let's try to understand what this means. So for a given capital X value, so specific capital X value denotes a material point, or we should say material particle. Okay, so you have a particle, and that the particle is referred through its position at t equal to 0, called its capital X, or the material coordinates. So a specific capital X value will denote some point, some particle, and t will denote some time. So density as a function of capital X and t will tell you, I mean, for a given value of capital X and t, will tell you the density of that particle at some given time. Okay, it's a physical property. It could be anything. It could be the force or the stress. So it's physical quantity. So it could be anything, any other physical quantity. So density can be specified as a function of capital X and t. Now, if I specify this density as a function for all possible values of capital X and all possible values of t, then I have given you the complete information about the density field. Okay, so you know the density of each and every particle, and at all the times, at all the configurations. So you know the density field completely. Okay, so we can express this density as a function of its material coordinates, and this expression of density, I mean of any physical property, in terms of its Lagrangian, in terms of its material coordinates and time, is called the Lagrangian description. Or we also use the word material description. Okay, so the words Lagrangian and material will be used interchangeably over the course of this discussion. Okay, similarly, we could have used a geometrical property or a kinematic property, for example, velocity. Okay, so as a function of capital X and t, I have the information about velocity. So I know the velocity of each and every particle at all times. So again, this is my Lagrangian description of velocity field. All right, so that's one way to specify that. The next one is, if I have density specified as a function of small x and t. Okay, let's use a rho star, because I'm talking about a different function here. So let's not confuse rho with the same rho. So what this means is, you specify some location in space or location in the room, because remember, our spatial coordinate system is always fixed to some room coordinates. So some value of x will denote some point in the room, and t will denote some time. So what this function will tell us is the density of the particle lying at that position in the room at that time. Okay, so if I give small x is 1,2, then it will tell me and some value of t, let's say t equal to t1. Then at t equal to t1, on the spatial location 1,2, whichever particle is lying, this function will tell me what's the density of that particle. Okay. So this description of spatial locations at all the times is called Eulerian description. Okay, as you may have guessed, it's named after the mathematician Euler. Okay, again, this is also used, we also use the word spatial description here interchangeably. Okay, so they contain the same information except that in different forms. Okay, so rho and rho star contain the information about the density at for all the particles at all the times. Similarly, we can have the velocity field v given as a function of small x and t. That will again be the Eulerian description. Okay, any questions on this idea? All right, so as a summary, what I can see is that, I mean, I have to decide which description to use, because depending on the situation, I may choose one over the other. So the first description, or the or the Lagrangian description, I tend to choose this one when my focus is on individual particles and what is happening to them at different times. On the other hand, the online description is more useful when we would want to know what's happening at some specific location in space at different times. Right? So let's look at an example. Example 422. So it says you'll have to find the velocity and acceleration of a given particle. Sorry, for a given spatial location. So you have the description of motion. So it's the same example that we discussed last time. Now we would want to find the velocity and acceleration. Sorry, I made a mistake. We will want to talk about example 432, not 422. Okay. So we have a Lagrangian description given to us. So now when we say Lagrangian, what that means is we have something given as a function of capital X and t. Because Lagrangian is in terms of capital X. So when we say description of motion, that means that we have small x given as a function of capital X and t. Okay, so the same function, the same description of motion that we've been talking about is nothing but a Lagrangian description of motion. Okay. So it's been asked to find the velocity and acceleration in both Lagrangian as well as Eulerian forms. So find the velocity field and the acceleration field in both Lagrangian and Eulerian descriptions. So what that means is you are asked to find V as a function of capital X and T and V as a function of small x and T, and similarly for acceleration A. Okay, so it's quite straightforward. I mean, finding the Lagrangian description is straightforward because V, as you know, is d small x by dt. So we already have the Lagrangian description given here. So all you have to do is you have to take the derivative of the right hand side with respect to time. Now we already know that capital X is not a function of time. So capital X can be taken out. So this becomes so I simply have taken the derivative of the right hand side here with respect to t, and capital X is a constant. Okay, similarly, you can take the derivative of this with respect to time again, and you can get the acceleration field in the Lagrangian description. For the Eulerian description, there's two ways. One is that you invert this function. So this chi is given to us. You use it to find chi inverse. Okay, so once you have that, you replace the value of capital X1, capital X3, and capital X2 if it exists, if it occurs. You replace them in terms of small x1, small x2, and small x3 using the chi inverse transformation. Okay, so that will give you the information. Or what you can do is you can start with the chi inverse function. You can take a derivative of that with respect to x. Sorry, no, that's wrong. So you have to use this is the only way. So you find the velocity field in terms of Lagrangian description, and then you replace the values of capital X1, capital X2, and capital X3 in terms of small x1, small x2, and small x3 using the inverse transformation chi inverse. Okay, so I won't do it here. It's a solved example in the book. You can go and refer to the book for details. Okay, next we talk about displacement field. So first we'll talk about displacement. So we have a reference configuration and we have a point capital A in the reference configuration, and we know that the position coordinate of this is capital X superscript A. Now after some later time the body has moved, so we have a current configuration where we denote the same point using small a because it's the current configuration, and the position vector of small a is given as the vector small x superscript a, and this displacement from capital A to small a is called my displacement from capital A to small a is called my displacement superscript a. So displacement of the particle A is denoted by u superscript a. So you can see that in the vector form I can write displacement like this. Now that's only for particle A. In fact, I can write the displacement field as small x minus capital X. Okay, so you put any value, any particle here. So this U field contains the information about all the particles that exist. Okay. Now the question is, how do I describe the displacement field? Because it's a field, so we can describe it using two forms. One's a Lagrangian form, or the Lagrangian description. That means my U as a function of capital X and T. So this will be written as small x as a function of capital X and T minus capital X. Okay. So it tells us about the displacement of the particle that starts at capital X. So you put any value for capital X, and it will tell us the displacement of that particle which was at capital X location initially. And on the other hand, we can have an Eulerian description, which gives U as a function of small x and T. So in the Eulerian description, U, or the displacement, refers to the displacement of a particle at that point small x at that time t from whatever its initial position was. So we don't know the initial position unless we form the unless we know the chi function. But U will contain the information of a particle at small x at a given time from its initial position, whatever it was. So that's the Eulerian description of the displacement field U. Now, if we take the derivative of U, that is, I write du by dt, then this is dx by dt minus d capital X by dt. Now, we already know that capital X is not a function of time, because capital X is the location of the particles at t equal to 0. So it has, it's independent of time. So this is 0. So what we are left with is the velocity v. So what it tells us is that the velocity can also be written as a derivative of the displacement field rather than the x or the spatial coordinate systems, the spatial coordinates of the particles. So we also, in fact, it's more common to write velocity as the time derivative of the displacement field. Similarly, you can have acceleration written as the second derivative of the displacement field. Any questions? At this stage, we can try example 441. So it says that you take the description of motion as in 431 and you find the displacement field in both Lagrangian as well as Eulerian descriptions. So I'll do it for you in the Lagrangian description. So if you remember, then let's do it only for 1. So U1 is written as x1 minus capital X1 by definition. Now x1, as it was given in the example, in the question, it was capital X1 e to the t plus x3, capital X3 e to the t minus 1. So if I write small x1 minus capital X1, this becomes x1 into e to the t minus 1 plus x3 . All right, so that's your U1 in the Lagrangian description. Now, as I said earlier, for the Eulerian description, all you have to do is you have to go back, you have to find the chi-inverse function and write capital X1, capital X2, capital X3 in terms of small x1, small x2, and small x3. Okay, that will give you the Eulerian description of U, or the displacement field. All right. So now we'll talk about the next topic, which is material derivative. It's a very important idea, so please pay attention. In case you have any questions, please feel free to ask them. So we also call material derivative as a total derivative. So if you have to understand it in one sentence, what this means is it's the time rate of change of any property if you measure that property sitting on some particle. So you attach the observer, because remember there's an observer that's measuring or it's making some measurement using a probe. You attach the observer to a particle and then you measure the time rate of change of the property. So let this property, for example, be temperature, which we denote using theta. So what we are saying is that the material derivative of temperature theta, what it means is you sit on some particle, hypothetically, you sit on a particle and measure the rate of change, the time rate of change of the property There is a time rate of change of temperature, and that is called the material derivative of temperature for that particle. Okay. So if I write theta in the Lagrangian coordinates or Lagrangian description, then the material derivative is your d theta by dt, where theta is written as in terms of capital X and t. Now we already know that capital X is not a function of time, so we can write this as del theta by del t, where theta is written in terms of capital X and t. Okay, so mathematically it's nothing but the partial derivative of theta with respect to time when theta is given in the Lagrangian description. And physically or intuitively, it's measuring a property, because you see that the particles are moving, the configurations are changing in time. So if you sit on any particle and let that particle be particle A, so then your capital X will be the position of particle A at t equal to 0. So if I put the capital X for particle A, then d theta by dt or del theta by del t denotes the material derivative of temperature for particle A. If I do it for all the particles, then I get the material derivative of the complete temperature field. It is also called the total derivative of the temperature field in this case. Okay. We sometimes also use capital D. You may have seen capital D by capital dt. That's also used for material derivative. Okay, so I hope the idea is clear, and that it's the rate of change, time rate of change of a property. But if you measure that property, if you measure the change sitting on the particle or sitting on some particle, which is denoted by capital X. Now, in many cases, it is more intuitive to use the Eulerian description of motion. So let me write in Lagrangian description. Okay. That means that your theta is given in the Lagrangian description or in terms of capital X and t. And you can see that the word material actually refers to the material description or the Lagrangian description. So it's basically the rate of change of theta with time if theta is given in the material or the Lagrangian coordinates in terms of the material or the Lagrangian coordinates. Now, as I said that in many cases, it's more intuitive to use the Eulerian coordinates. That is, theta is a function of small x and t. So in that case, when you write d by dt of theta, so I mean, using chain rule, you can write this as partial derivative with respect to t of theta plus so we have used chain rule. So I've written d by dt of theta as the partial derivative of theta with respect to time. And I've used initial notation here. Instead of writing the x vector, I've used x subscript k. Okay, so that's the first part. Now theta is also a function of xk. So we write this as del theta by del xi of xi comma t times dxk by dt. Okay, now xk actually is x1, x2, and x3. So theta is a function of all x1, x2, x3, and t. So you can expand this, and this is what you will get. So this idea should be clear from your vector calculus. So this is the using the chain rule. Okay. Now the first part on the right hand side, this part we call the local rate of change. Okay, so what this means is that let's try to revisit the definition of partial derivative. So it's saying that keeping your xk, small xk fixed, you take the rate of change of theta with respect to time. Now when I say if I keep my small xk fixed, that means you're keeping your spatial location fixed. If you keep a spatial location fixed, that means you're fixing the probe in space. So you fix the probe at location 1, 2, for example, and when you fix the probe, then you measure the rate of change of theta with respect to time at that spatial location. That's the meaning of this first term, local rate of change. We use the word local because it's fixed in space. So local refers to fixed in space. Now the second part is called the convective rate of change. Okay, so the word convection refers to flow because it's some property being changed because of flow. So here what you're seeing is that you have a term dxk by dt, and that is nothing but your velocity field. Okay. So I mean, of course, you're measuring that at position xk. So what you're saying is that it's the rate of change of theta with respect to x. So that's the gradient of theta. So there's a temperature gradient in space, and you have a flow happening. So if you measure that rate of change because of some flow, so that will correspond to some temperature that you some temperature change in time that you see because of flow. So if you have a flow at a given point in space where some hot fluid is flowing in the beginning, then you have a cold fluid, then you will see a rate of change of temperature because of the temperature gradient and the flow. If any of these two quantities is zero, then convective rate of change will be zero. That is, if there's no velocity, no flow, then there is no convective rate of change, or the temperature gradient is zero. Temperature is same everywhere. So if you have a hot fluid at a given point and more hot fluid replaces that hot fluid, then you won't see a change in temperature. Okay, so in that case, the temperature gradient is zero. Even then, the convective rate of change is zero. So that's the second part of your Eulerian description of material derivative. Okay, now I've seen in almost all cases there is some trouble understanding the idea. Again, I mean, you will have to revisit this idea again and again to reinforce it. So don't be tensed if you can't understand it in the first go. So till now, what we did was we simply mathematically wrote the derivative of theta with respect to time using the chain rule. That's what we have done. We haven't tried to understand the physical meaning of that, other than calling the first term as a local rate of change, the second term as the convective rate of change. Okay, so we will spend more time in the future on the physical interpretation of this idea. So what we see here is the theta was just, I mean, some variable that we have chosen. It could be a tensor field as well. So this a material derivative can be applied to some tensor field P, which is an nth order tensor. So what we say is that the material derivative in the Eulerian form Okay, I'm sorry, I made a mistake here. So this was xk, and this is dxi. So in general, we can write d by dt as del by del t plus vi del by del small xi or something. Or in the symbolic notation, we can write this as d by dt equal to del by del t plus v dot grad of something. Okay. So they are all the same. This is the symbolic notation, and this is the initial notation. So that's your Eulerian description of motion. Of material derivative. Okay. Now I can give you one quick example, and that will make things clear, because remember that it's a material derivative on the left hand side. So this is your material derivative, which we actually defined as a property that you measure by sitting on some particle. So your question would be, how is that property measured by sitting on a particle same as the sum of these two quantities, local rate of change and convective rate of change? So what we'll do is, firstly, we'll give an example. So the question is, how is the rate of change of theta measured by sitting on a particle the same as the sum of the local rate of change and the convective rate of change? So the way we will understand this, first we'll understand it intuitively, second we'll do it rigorously mathematically and show that this is indeed the same.